For the MOS differential pair, the RN equals infinity. Big RO is RO2 or RO1. They should be the same. And the voltage gain is GM1 or GM2. They better be the same or the circuit doesn't work, times big RO. If I have this stage in my circuit and I have something else connected to it, I can use that two-stage model of the amplifier and I can figure out what the overall gain is of a two-stage circuit without having to look at all those horrible transistors in there. I can model it as an input resistor, an output resistor, and a gain, and not have to think about the transistors. Common mode rejection ratio. We had a time with that, didn't we? This is what I really want you to know. And this is what every engineer should know about common mode rejection ratio. It's the differential mode gain over the common mode gain. You want it to be high because you want the differential gain, that's the signal gain, to be high. You want the common mode gain, which is the noise gain, to be small. So typical values of CMRR for a op-amp, 100 dB. That's typical. If you're really looking for a high CMRR, you can find a few that have 120 dB or 140 dB. Be careful with this. If you care about high frequency noise, the common mode gain is dominated by a 0. So it's going to start going up at some frequency, which is lower than where the gain bandwidth product of the amplifier is. So op-amps typically reject low frequency noise better than high frequency noise. But really what I want you to know is can you do that? Frequency response. Okay. There's one problem on there. No, it's not the 2-pager.
Is it a Bodie plot?
It's not a Bodie plot. I think even after I do this, people miss this problem. This is everything you need to know. This is the most important thing right here. We're going to kind of like ignore inductors. Tau is dominated, usually it's an RC time constant. So your time constant is RC. If I want to calculate the frequency of the pole associated with this R and C, F equals 1 over 2 pi RC. If you see a problem on the exam, please don't miss this. If you see a problem on the exam that gives you an R and gives you a C and asks you what the F is, 1 over 2 pi RC. It's like the thing that yeah. How many arguments do I win with people over stuff like this? How many young engineers can you just 1 over 2 pi RC? Remember that. CMRR, differential gain over common mode gain. CMRR, good. We want it big. Yeah, you're going to be, yeah. Yes, there is a data converter problem. I'll give you a hint. It has something to do with an R2R DAC. Remember, okay. This will get to me too when I'm grading it. I'll forgive you after I get done grading it, but I'll be mad at you while I'm grading it, or I'll be frustrated. I won't know whose paper I'm grading. That will be helpful. Okay, so remember what we did here. We set this thing up so that the REQ looking into here is always 2R. 2R. And because of that, we can use the voltage divider rule, and we can go through and figure that out, is that basically I've got VREF and 2R that is right. 2R in parallel with 2R is R. We've got an R here, and I've got a voltage divider between R and R. So this is going to be VREF over 2. The next one down, I have that same voltage divider, so this is Vref over 4. V2 is Vref over 4. V1 is going to be Vref over 8. We can use this network to build a DAC. Remember this result. When I get to this circuit right here, let's just do a 3-bit one right here. We'll join this up and call it a 3-bit one. N equals 3. Now, when I look at that ladder network, this is an R2R network. You could go through and do the analysis, or you can just kind of remember for this R2R network, I've got 2R, I've always got 2R looking into there. So this is going to be, when I go to this next node here, this is going to be Vref over 2, just from that previous analysis. I don't have to think about it. I can just write down these node voltages. Vref over 4. Now I've got a, this is, yeah, it is. This still works. Okay. I've got this thing set up. Now the current going through these resistors. Let's just pull one of these resistors out. On one side, I have Vref over N. The other side of the resistor, well, it may be tied with a switch to ground, or it may be tied to a switch to this negative terminal. We know the resistance here. Okay, what's the voltage at the negative terminal? Thank you. It's ground. That's a really important thing to remember. This is like the golden rules of op amps. If you know the voltage at one terminal, the voltage at the other terminal, your first guess is it's ground, or it's the same voltage, or it's V offset. So this is 0 volts. So now I know this resistor here has a choice of being tied to ground or being tied to ground. So no matter what, this is tied to ground. Can you calculate the current through that resistor? Oh, I said 2, I meant N. The current through that resistor is Vref over N. V equals IR, it's V I over R over 2R. That's the current. All the current, now, if the switch is in a position like here, then the current through that resistor, it can't go into here. Infinite input resistance, just like a diff amp. All that current has to go through this resistor. And the voltage output is going to be V out. Since this is 0, got the voltage drop across the resistor. V out minus 0 is going to equal I through the feedback resistance. That's that little R right there, times R. V equals IR. You can calculate pretty much everything from the circuit just using Ohm's law. If you know that as you go across the ladder, you're going to drop down by a factor of 2. And that if you know that the voltage at both terminals of an op amp is 0. It's not 0, it's the same. In this case, it's 0. So pay attention to that. Okay. That's all I want to say about DACs and ADCs. Oh no, I do have the last slide. Last slide. I'll survive. Oh, it's time to go too. Do you know how to measure them? I'll just tell you right now, this isn't on the exam. So I can go home. I'm done. And I'm frozen. No, I'm not frozen. Okay, I will be in my office. I do have a lab meeting tomorrow afternoon. I won't be answering my Zoom or my email during the lab meeting, but I will be in my office Friday morning mostly. I'll be in my office Monday. I'll be in my office Tuesday, and I'll be in my office Wednesday. And if you have to get a late lab to me, you better do it tomorrow. Okay. All right. It's been fun. Yeah, thank you. It's been fun. I really enjoyed this class. I've liked having a smaller class in here. Even though very few of you, most of you are black squares. I hope to see you all in person this fall. And this is the last class you have to take from me. After this, you can just choose to like never see me again if you want to.
Or you can join 490 in the fall.
Or you can join 490 in the fall, which is now a viable class. I've got like 10 people enrolled. I've got 10. And both Michael Garcias are going to be in there. It is. And well, you don't know. You want to know what room my 490 in the fall is scheduled for? It's in the Castro building.
Oh, is it the big one?
No.
Yes,
How is that going to work? I need.
A field trip to go.
We need to take a field trip to go to the lab.
Wait a minute. Yeah, I was like.
I've emailed the scheduler. He hasn't answered me yet.
I was like, I was thinking about that.
I go, I usually do it in 234, but I'll take 235. And I would even do it in the IEEE room above Castro. And then just come in here and steal equipment.
I was like, first assignment, get an IEEE code.
Get an IEEE. Okay.
Get one fit there.
All right. I'm going to stop recording.